Welcome back, everybody. In this video and the following next few, I want to slowly introduce you to the next larger topic area in this course, which is going to be intra-procedural static analysis. And in order to explain to you what the difference is to what we've seen so far, let me briefly recap what I taught you in the previous week. You learned about intermediate representations and how they can abstract from concrete input languages. In particular, we talked a little bit about the Gimple IR, the Gimple intermediate representation, which is an intermediate language in 3 address code format. But there are also other often quite similar IRs that can be used for the same purpose. For instance, Phasor and LLVM, they both use the so-called LLVM IR, which is a bit more low level, but it shares a lot of the properties of Gimple. Then we also talked about type systems, which allow one to determine mostly flow-insensitive program properties, like I showed you through constraint generation and resolution using a unification solver. So I showed you this picture here. The general idea is you have some abstract syntax tree, so a syntactic representation of your program. Out of that, you generate some type constraints. You then put them into this unification solver, and in the end, you get a solution if the program does type check. Or if it does not, then you will also get some information about what constraints are violated. Now, in this week and the next, we are looking at intra-procedural static analysis. And here I want to focus now on flow-sensitive analysis. So the general setting is still the same. As an input, we are still receiving a single method of an application or some program code. And we still want to determine some property, whether that holds in this method, and that's going to be determined by our static analysis. What's different here is now that really we want to make sure that this property holds or does not hold at a certain statement X. Okay, so we have some specific statement in this method, and we want to know is this property true or not at that given statement. That is what flow sensitivity is all about. So we really look at the program order and we determine different properties for different statements in a flow insensitive analysis, and therefore also in most type systems, that is not the case. And there are a number of example properties that are interesting in that regard. And here's just a brief list of what might interest you. So for instance, often you want to know, is a certain variable still being used later on? And this can be decided, for instance, by a so-called live variables analysis. Why is that important? You can think about that for a few seconds. Well, for instance, it's an important property to decide in compiler optimizations, right? So often when a compiler wants to make a program execute fast, it tries to allocate as many local variables as possible into registers, for instance, right? Because registers can be accessed really quickly. And then, of course, it's interesting to know how many variables are live at the same time. Can I still all put them into registers, or do I need to spill them into other memory locations? Another interesting question is, can this code ever execute? And that is done using a so-called dead code analysis. And we already saw an example of this when I was talking about this go to fail bug that Apple had a few years ago. And that also is naturally a flow sensitive analysis, because that code is typically dead because it's guarded by a certain if statement, a certain conditional that can never be true. And so the code after that if statement is dead, and the code before the if statement is then oftentimes still alive. So we have a property that's certainly flow sensitive. Also, can this pointer ever be null? That is decided by a so-called nullness analysis, and very often, at least, that also only makes sense as a flow sensitive analysis, because obviously most variables, they are assigned a value or an object at some point. But initially, that may not be the case, or at some point, they may also be nulled out. And then that property changes, right? So also that makes mostly sense for a flow-sensitive analysis. Also things like, is this file handle ever closed, right? So you are looking at a file handle. Maybe there's a certain method that needs to be called in order to close it eventually. And you want to close it so that it doesn't remain open and depletes resources on your computer. And this is decided, for instance, by a so-called type state analysis. So a type state tracks some internal state of an object throughout its lifetime, and that can be used to model certain calling sequences on objects. And we will still be talking about many of these examples later throughout this course. What's important now is that actually all these flow-sensitive properties here, they can be solved in a somewhat similar fashion, so somewhat similar to what we have discussed so far. So the picture that you are seeing here, it doesn't look all too different from what you already saw, but there are two crucial differences. So first of all, we are still generating constraints and we are still solving them to obtain a solution. But there's one big difference when it comes to the input. So the input is now no longer an abstract syntax tree, but it's actually a control flow graph. And in this setting where we are talking about an intra-procedural analysis, so an analysis within a single procedure, it's actually still a control flow graph that is restricted to a single method only, right? To a single procedure only. Later on, we will also be seeing settings where we do this inter-procedurally, so where it spans multiple procedures at the same time. Like you can see here, these control flow graphs, they can have cycles. And as we will see later, that can give some complications when it comes to actually not only building up constraints, but in particular solving them, because you can have recursive dependencies. And that introduces some challenges to actually solve these constraints. And therefore, they are also not being solved by a unification solver anymore, but like you see here on the right-hand side, by a so-called fixed point solver. And that's something that we will also be talking about extensively in this week and the next. But conceptually, you can still separate this constraint generation from the constraint solving. Yet in implementations, the two stages are usually interleaved, and we will be talking about rather efficient algorithms also throughout the entire course, actually, that do interleave this heavily in order to actually gain better performance of the analysis. Okay, in order to get us started, let us just look at a very simple example to see how that could actually work in principle. Let's assume we have some example program here. It's not doing any really sensible computation, but it is computing some numeric values, like you can see here for these variables z and x and y. And now we may be interested in asking this question, which of these variables can actually carry constant values and at which statements? And if they do so, which values exactly do they actually carry? And there's actually a type of analysis called constant propagation that decides exactly that. Now, the first thing that we will do is, because this is the syntax that we are looking at, so this is basically an abstract syntax tree, we are going to turn it into a control flow graph, like you see on the right-hand side. And what we will assume here, and also for pretty much the remainder of the course, is that the static analysis that we execute is ignoring conditionals. There are certain kinds of static analysis that do actually look at conditions and try to match conditions against one another. For instance, in that code analysis, that is important to figure out whether code is actually dead or not. But most other static data flow analysis, they ignore conditionals completely. So they basically assume that if you have such a branch, it could go along here, but it could also just as well go along here. We don't really know about it. And we are also going to make that assumption, at least for the next few lectures here. Okay, then let's take a look at this control flow graph more closely. we want to determine what can be possible constant values in this program. And now what we are doing is essentially something that in program analysis is also often called abstract interpretation. So we are sort of interpreting for ourselves what this code would do if we were to execute it. And let's assume at the beginning that all the variables that you see here, they are implicitly initialized to 0. So we have such a mapping or an environment that initializes x and y and z to 0. And now we can think about what changes to that environment when we execute the first statement. Well, quite obviously, the value of z is going to be changed from 0 to 3, right? So we get a new environment that just looks like this. And then we go to the next statement, and now x is no longer 0, but it's actually 1. And now let's assume that we actually first go to this branch here, and nothing changes here, of course, but the value is propagated to just before that particular condition here. Now what we can assume here is that we actually are processing this particular assignment here, right? So y is now actually 7. And now on the right-hand side, something interesting is happening now actually for the very first time. What you can see here is that we have an assignment to the left-hand side y, but the exact value that is being assigned actually depends on this other variable z on the right-hand side, right? And this means that in this particular statement, we have a dependency, right? The value that is being generated here depends on some other previous value that has already been computed as part of our environment. And if you look at the environment here, then we currently have the assumption that z is pointing to the value 3. Okay, and we are adding 4 to it, and the result we are actually assigning to y. So that means also in this branch, y is actually going to point to the value 7. So just coincidentally, we have the same environments on both sides here. That is nice for us because now it's actually really simple to merge these two environments, right? So we have the same on both sides. So if we now want to determine what is the right environment to put down here, well, it's actually this one, right? So the value of z is still 3, like on both sides here. The value of y is 7, like on both sides here. The value of x, though, is naturally being updated due to that assignment that we saw here. Now the next interesting thing is happening. We are next wrapping around the loop. So this particular value will be propagated backwards here. And now we again have a situation where we have two control flows that meet. So we actually have to merge analysis information now. But now the analysis information is different for the two branches, right? So we have this one environment, this one mapping that comes from the top, and we have the other one here that comes from the left-hand side. And now it's not so trivial anymore to decide how these should be merged, right? And how you merge in such an analysis, it really depends on what you are after and what the analysis is trying to solve. But here we said we want to have information about variables that are actually constant and carry a constant value. And if you now look at these two environments, you will see that there are actually two variables, namely x and y, that do not really have a constant value at this program point, right? Because depending on where you come from, whether you come from here or there, the values for x and y, they're going to be different. So they're definitely not constant. And therefore, what one typically does in this case is one simply removes non-constant values. So the environment will shrink, and we will, in the next iteration, for this program point, only retain the mapping z equals 3. Okay? So that is the sole constant value that after the first iteration we have at this program point. Now this is being propagated further down, and again here we now get a new value for y. We can still determine that because we have a value for z. At this branch, y is still constantly going to point to this number 7. The same is obviously true also for the left-hand side, because here we do have a constant assignment. And now the following happens. We still coincidentally have the same mapping on the left-hand side as we have on the right-hand side. And we will merge this before the statement to the same mapping, y equals 7 and z equals 3. And then because x also equals 3, we are going to be arriving at the same mapping, at the same environment that we already had earlier. And what this means now is we have generated information at the very same statement that we have seen already before, right? That piece of information is the same as in the previous iteration. And whenever that happens, at all the program points, we say that we have reached the so-called fixed point. So basically, by induction, we can now know that if we were to propagate this further through the program, we would have to get the very same information again and again and again. So nothing would change anymore. And I will later on show you how we can make sure that this is really the case. So there are certain mathematical principles. In particular, we will be working with so-called lattices that ensure that if we have such a situation where we basically get the same information in the analysis that we have seen previously, then we are guaranteed to have reached the fixed point and nothing will change anymore. And when we have this scenario, we can then simply stop the analysis. It has basically completed. And this is our final analysis information. So what this would now tell us is that, for instance, at this program point here, we definitely know z has the constant value 3, but x and y are not constant. But at this program point here, for instance, y is also constant. It definitely has the value 7. So much about the example. Of course, the big question is now, that's just an example, right? So how can we find a more general concept to analyze programs, right? We want to do that not just for a single method. We want to do that for all the methods you can think of. And we also don't want to do it just for constant propagation, but I told you about all these other interesting properties that we might want to solve. Now, there is a naive non-solution that I briefly want to talk about because conceptually it's sort of the optimal solution that you could think of if you were to be able to compute it. So let's take a look at this program again. And now let's assume that we want to compute in particular the constant values that we have at this program statement here, okay? And now conceptually what the so-called MOP solution, the mean overall path solution computes is the following. So it's basically telling us, okay, let's compute possible data flows along all the potential paths through the program. So you see this one path here that goes along the left branch of the if then else. Then you have this other branch that goes along the right-hand side. But then obviously you can have other paths that lead you also through the loop, right? So we could go along the left and go through the loop once, but we can also then go, for instance, to the right-hand side of the branch, and so on and so on. And you can see that even in such a simple program here, very obviously there is an infinite number of these paths, right? And that happens as soon as you have loops. And you can't really do anything about it. So in order to determine how often this program would actually go through a loop and then into which branches, we would really need to statically evaluate these conditionals here. And you can very easily show that while you might be able to do that in some special cases, you can never do that in general because that is an undecidable problem. So it's just uncomputable. You cannot find a program analysis that would determine in all and every situation what the conditional might be, whether it's true or not. And there might even be some conditionals, that are simply true always. So for instance, if you have a server application, it's typically programmed with a while true loop. So it will always wait for additional responses. And then further down within the loop, you might have a certain conditional that then, leads to some termination of the loop later on. So that all means, yes, there is such an MOP solution, and it's actually defined like this. We basically assume that we have, so first of all, we want to compute the MOP solution at a given statement, right? So for instance, this one assignment statement that I showed you earlier. And we are computing it over every path P, that is a path from some initial statement of the procedure to that particular statement we are interested in. And then we are basically computing the MOP solution path by path. So we are computing a data flow function that represents all the data flow effects of all the different statements on this path P, assuming some initial value I. So we are assuming some initial assignment, like I showed you here, x equals 0, y equals 0, z equals 0. And then we are applying some data flow function for the entire path to it. And then at the end, we are executing a so-called meet, or also you can call it a merge operation, over the results that we get for each individual path. So conceptually, that's the idea, right? So we compute a solution one path after the other. We do it for all the infinite paths, all the infinite numbers of paths that are out there. And then we do a really large or infinitely large merge over all the results that we would get out of this. Okay. Yeah, that's just for you to read up at home. So here's the composed flow function, and there's the initial value. Unfortunately, the MOP solution is really uncomputable in general. And you can prove this through a formal proof that is actually reducing this problem to the so-called post-correspondence problem. That's something you would be able to look up in the literature. So that's a simple reduction proof to another undecidable problem. But like I explained to you, also intuitively, it's just not computable because this problem of deciding conditionals is actually undecidable. And there's actually a more general result to this, which is called Rice's theorem. And that's really unfortunate, like I said already, right? So any non-trivial property of the behavior of programs in a Turing-complete language is undecidable. And hence, for any given program analysis algorithm, let's call it A, you can always find a program P for which A applied to P, so the analysis applied to the program will yield the wrong result. So that's just, that's just something that we have to live with. But as I already said, that also makes it interesting, right? And so we seek to ensure that the answers that the answers that A actually will yield, right? So that the analysis actually will yield, they are at least approximative. So that means, in other terms, they are sound. And when we say that, we mean that the analysis, it will rather err on the safe side. So whenever the analysis does give you a result at a certain statement, the analysis should be sure about that result. And if it's unsure, like for instance in the constant propagation, there might be a situation where a value actually is constant, but the analysis can't quite figure it out, then it should rather report it as not being constant. And there are other examples of sound approximations. So for instance, let's assume we want to decide if a given function is ever called at runtime. So if the answer then is no, then we would, for instance, be able to remove that function from the code, right? So it would essentially be dead code. And if it's yes, if it is called, then we wouldn't do anything. So that could be a use of a static analysis in a compiler optimization. But if we have that setting, then the no answer must always be correct if given, right? So we really must make sure that this is treated soundly. The other way around, if we want to decide if a cast, so a cast of X to some type A, will always succeed, then we could also have an optimization that says yes, if we know that it will always succeed, then here at this cast, we actually would not generate a runtime check, right? So we know that this cast is always okay, so we can simply not do anything, basically, right? So it could be translated into a NOP operation. But we really want to make sure that this yes is actually correct, because otherwise you could coincidentally be generating type incorrect programs that at runtime actually propagate objects to memory locations that were never prepared to hold objects of that type. And then you can actually have vulnerabilities that exploit such incorrect typecasts. So here the yes answer must always be correct if given. And yeah, that's all I wanted to say about a brief introduction and motivation for intra-procedural flow-sensitive static analysis. In the next video, I will be talking about how we can systematically address that using the so-called monotone framework. So that's a general framework that actually allows us to encode and then also solve such kinds of analysis.